Okay, so when we last left off, we talked about reading solubility curves. Now in this session, we're going to focus on quantifying and quantitative measures of solution concentration. So one of the common ways that solution concentration is represented, because it's relatively easy to prepare these solutions, is to express solution concentration in terms of mass percent. So what is mass percent? Mass percent, just like our typical mass percent formula, is the mass of our part, in this case the mass of our solute, over the mass of our solution. So the mass of the solution is the total mass of the solute and the solvent, right? You have to account for the total mass if you're writing a mass percent expression. When you see percent by mass, it's best to think of it as the grams of solute per 100 grams of solution. Does this form look familiar to everyone? Does this conversion factor look familiar from our chapter on mass percent? It's exactly identical, except it's per 100 grams of solution. Now, things are best learned by application. So let's talk a little bit about how we would calculate the percent by mass concentration of sucrose that's made by dissolving 7.6 grams of sucrose in 83.4 grams of water. Okay, so what is our solute? What is our solute in this case? Sucrose or water? Sucrose, yes. So what mass of sucrose do we have? Yep, 7.6 grams. What is the grams of our solvent? What mass of solvent do we have? Yep, 83.4 grams. So in order to calculate the mass of our solution, so the grams of our solution, it's equal to the total mass of solute plus solvent, which is 7.6 grams plus 83.4 grams. And if we punch that into our calculator, that in turn gives us 91.0 grams of solution. Now we are ready to calculate the mass percent. So then, if we want to calculate the mass percent of sucrose, we need to take the mass of sucrose, which is what? So, what's the mass of sucrose? 7.6. And then we divide by the mass of our solution, which is 91.0, and then we multiply by 100%. The units of grams cancel, and we're left with a unitless number. And that in turn gives us 8.35% that we round to 8.4% to follow sig fig rules. Did everyone get the same result in their calculator? If you need me to do any of the calculations on the document camera calculator, just let me know. Does that example make sense to everyone? So what I'm now going to do is I'm going to let you loose on the following second example. I'd like you to tell me how many grams of sucrose need to be added to 375 grams of water to prepare a 2.75 mass percent solution. And be very careful with this problem, because you need to consider the mass percentage is the mass of solute over the total mass of solution. So you may need to use some algebra. So I'll be walking around to check to see how it works. Yeah, exactly. We'll just solve it. Everything going on? For 100 grams of solution. But that's not the grams of solution. That's the grams of salt. But you're very good on the right track. Try to write out, like, just like you did in the first example, all the grams of salt, grams of salt, what the mass of solution look like, what the mass of expression look like, and then look at the is this 375 the mass of solvent or the mass of solution? So it'll be a little bit more tricky. Yeah, that's just don't create those times. Otherwise, I'll do a solve. Yeah, and then turn the expression for the mass of solution. Just solve. That's the everything going. Yes, exactly. And in fact, it's not solid, it's not solid. Otherwise, the structures. Is the 375 is the mass of solid. So I saw a lot of reasonable solutions for, that's a bit of a pun, but I saw a lot of reasonable answers to the following expression. So let's talk a little bit about this. So my grams of solute, I don't know, so I'm going to write it as X, just as a placeholder. My grams of solvent, my mass of solvent is water, so I have 375 grams. The mass of my solution, the total mass of my solution, is equal to the total mass of solute plus solvent. So I have X plus 375 grams. Now this is really critical. The mass percent equation is the mass of solute over the mass of solution. So mass percent is equal to grams of solute over grams of solution times 100%. So plugging that in, our grams of solute is X, our grams of solution is X plus 375 grams, times 100%, and are we given the mass percentage? Yes. Yep, it's 2.75%. Okay, we're now ready to solve this expression. So 2.75%, we're going to divide both sides by 100%. So 2.75% divided by 100% is equal to X over X plus 375 grams. What we're next going to do is we're going to multiply both sides. We're going to multiply both sides by X plus 375 grams. Okay? And that in turn gives us X plus 375 grams times 0.0275 is equal to X. Okay, so this is just algebra, but I'm showing the steps for each portion. I'm then going to distribute each of the terms, so 0.02275x plus 10.3125 grams is equal to x. I'm then going to move this x term to the left-hand side via subtraction. And we get 0.9725x is equal to 10.3125 grams. I'm going to divide both sides by 0.9725. And that in turn gives me a value of x of 10.3125 divided by 0.9725, which gives us a value of 10.6 grams. So this is how much solute we'd need to add. Did everyone get a similar answer when they computed it out? And we can actually check our work for this answer by plugging it into the top expression. So if we plug in 10.6 over 10.6 plus 375 times 100%, let's see what we get. We get a nice clean number of 2.75%, which matches our reported value. Does that make sense on how you can check your work? So this problem is a little bit more difficult than the one that we did first, but the reason why I included this problem is because it really showcases you need to read these equations carefully and plug in the right numbers. You can't use the grams of solvent as the entire mass of the solution. The mass of the solution is solute plus solvent. Does that make sense? Any questions on this example? If not, we'll continue on with our next type of percent expression. So another way of expressing solutions, which are often mixtures of liquids dissolved in another liquid, is volume percent. So it's the volume of solute over the volume of solution, so the total volume. And just like the total mass, the total volume of our solution is the volume of the solvent plus the solute. You can also think of volume percent as a conversion factor of milliliters of solute per 100 milliliters of solution. Or you can also think of it as liters of solute per 100 liters of solution. Does that make sense to everyone? Okay. So let's do an example. Let's try to answer the question, how many milliliters of solute are needed to make 2.35 liters of 25.6% volume percent ethanol? That's not exactly drinking grade ethanol, but nonetheless, you may have need for that solution as like a disinfectant of some sort. Okay, so let's write what we know. What is the volume of our solution? What is the volume of our solution? Yep, 2.35 liters. So we have the volume of solution already given. Do we know our volume percent? Yeah. What is the volume percent? Yep, 25.6%. I also like to think of this as 25.6 liters of ethanol, which is our solute, per 100 liters of solution. And this is really a setup to help us use this volume percent as a conversion factor. So given the volume of solution, we want to convert to the volume of ethanol. And as we establish, what's our conversion factor that allows us to go from the volume of solution to the volume of your solute? What conversion factor has the form? What has the form, if we want to go to the volume of ethanol, what conversion factor has the form volume of ethanol per volume of solution? What do we call this conversion factor that we're going to be using? Volume percent, exactly. So volume percent, just like mass percent, is a conversion factor that allows to go from the total volume to the volume of a component. Okay, so let's now execute on that. So we have 2.35 liters of solution, and my question to all of you, if we're going from the volume of solution to the volume of ethanol, what goes on top? Volume of ethanol. So we have 25.6 liters of ethanol per 100 liters of solution. And then finally, since the problem asks for milliliters, in 1 milliliter, we have how many liters? What does the milli prefix correspond to? Yep, 10 to the negative third. Okay, so let's now punch this into our calculator. So we have 2.35 times 25.6 divided by 100 divided by 1 EE negative 3. And that in turn gives us 602 milliliters if we're accounting for the 3 sig figs given in each of our inputs. Did everyone get a similar answer punching it into your calculators? You're going to want to make sure that that you're able to punch each of these expressions into your calculator, since you don't want to lose 1 point to 2 points on every single question to calculate errors, because that can add up to an entire letter grade with a point. So just make sure you're practicing your calculator inputs. Does this make sense to everyone? Let's now have you try an example so I can observe and get a sense of how everyone's doing on this topic. So to accomplish this, I'd like you to tell me what volume of water is needed to prepare a 10.6 volume to volume solution of acetone containing 10 milliliters of acetone. And this one, just like our mass percentage example, may require you to use algebra. One correction, when I was reading through the calculator, for the previous example, it should be 60.2. No, wait, let me check one more time. 2.35 times 25.6. No, 602 is right. Oh, I was just checking someone's work. Let me. Okay. Is this divided by the volume of solvent or the volume of solution? So does the volume of the solution include the acetone? So then we have to change the equation. Everything going okay? Or do you have a question?
Same as
the mass percent.
Yeah.
So you have to write out an expression for the volume of solid and then the volume of solution.
Yeah, that's the same, just in terms of
Everything going okay? The only thing is, in order to solve for the volume of water, you're going to need to write out an expression for volume percent, and then solve for the volume of water. Everything going okay?
Yeah.
So let's talk about this example. This is an example that's very similar to the mass percentage example. So we're asked what volume of water is needed to prepare a 10.6 volume over volume percent solution of acetone containing 10 milliliters of acetone. So what is the volume of our solute? What is the volume of our solute in this case? Yep, 10 mLs. Yep, exactly right. Do we know the volume of our solvent? Do we know that? Do we know the volume of our solvent water? No. So we're going to write it as X. The volume of our solution is equal to the solute plus the solvent, or 10 milliliters plus X. Okay. We also know that our volume percent is 10.6%. So we have all the information we need to write an equation that we can solve. So we know that 10.6% is equal to the volume of our solute, which is 10 mils, over the volume of our solution, which is 10 milliliters plus X, times 100%. Okay, from this, we can now solve it algebraically by moving over the bottom term and the percentage term. We in turn get 10.6% divided by 100 times 10 milliliters plus X is equal to 10 milliliters. Okay, then from there, we're going to distribute each of these terms. And let's now write this on the right-hand side. So let's distribute each of these terms. So we have 1.06 milliliters plus 0.106x is equal to 10 milliliters. We then have 0.106x is equal to 8.94. And to finish off this algebraic solution, we just divide by 0.106. And in turn, we get a volume of water of 84.3 milliliters. So once we have this set up, it just turns into algebra. Does that make sense to everyone, the logic behind it? This one's actually a little easier than the mass percentage because X is only in one portion of the expression. Any other questions on this example before we move to our third type of concentration expression? Don't be shy to ask. This is really for everyone to air out any questions that they have. And if there's any part that you'd like me to explain in more detail, please don't hesitate to ask. If not, well, then we can continue on. So then, the last major measure of solution concentration and solution composition is mass volume percent. It is of the form gram per milliliter. So mass volume percent is the mass of solute in grams over the volume of solutions in milliliters. Okay? You can think of it as the grams of solute per 100 milliliters of solution. So let's do an example together. So a typical saline solution that's used in hospital settings is 0.92% mass over volume sodium chloride in water. We are asked how many grams of sodium chloride are required to prepare 35 milliliters of solution. So what is the volume of our solution that we are trying to generate? Are we given the volume of our solution? How many mils of solution are we trying to make? 35 mils. So we know the volume of our solution is 35.0 milliliters. That we know. Okay. Do we know the mass over volume percent? Do we know the mass over volume percent? Yep. So 0.92%. Especially for those going in the medical field, you want to be able to know how to calculate the amounts needed to prepare different solutions, because if you get this wrong, a 9.2% saline solution is quite dangerous to give someone. So then, now that we have both of these pieces of information, we know that the mass over volume percent, which is equal to 0.92%, is equal to the grams of solute, which is sodium chloride, which we'll call X, over the volume of solution, which is 35.0 milliliters, times 100%. Okay, now in this context, with this information established, we can now solve for the grams of sodium chloride. Another way to think about it is we can use this mass over volume as a conversion factor. This is essentially saying we have 0.92 grams of sodium chloride per every 100 milliliters. I like the conversion factor method because it's easier to write one-line solutions. So we're essentially going from the volume of our solution to the grams of sodium chloride. And what conversion factor are we going to use to get from point A to point B? Sorry. Thank you. Okay, so what conversion factor are we going to use to go from the volume of solution to the grams of sodium chloride? What conversion factor allows us to go from the volume of solution to the gram of solute? So density allows to go from the mass of a substance to the volume of a substance, but what conversion factor do we have that's written right now that's of the form grams of sodium chloride per milliliters of solution? Yes, and what do we call that conversion factor? Would anyone like to? Yep, the mass volume percent. So all of these expressions of concentration that we're talking about are new conversion factors you can use when we're dealing with solutions. So with my solution map established, given that I have 35.0 milliliters of solution, if I'm going from the volume of solution to grams of sodium chloride, what needs to be on top? Grams. And I have 0.92 grams of sodium chloride per every 100 milliliters. And that in turn gives us 35 times 0.92 over 100. That in turn gives us 0.322 grams of sodium chloride that we round to 0.32 grams of sodium chloride. Many of the calculations for intravenous dosing are done as mass volume percent, and there have been cases where nurses have either miscalculated and misadministered the dosage in mass volume percent and ended up giving a super concentrated solution to patients. So these calculations are very common in the medical field for preparations. Any other questions on this? Okay, we're now going to get to the by far the most common way of expressing concentration in chemistry, which is molarity, right? We want to express concentration in terms of moles. We can handle and do a lot of things with moles rather than mass. So molarity describes the moles of solute per liter of solution. So molarity is of the form N over V, or mole per liter. Okay, a shorthand way of expressing concentration is to place your species in brackets. So for example, if you have Cl minus in brackets, we're describing the concentration of chloride. And that's the convention your book will use throughout, especially in 102. You should also know that we can express molarity using prefix units. So for example, millimolar, instead of describing moles per liter, describes, instead of moles, if we have millimolar, we describe, so instead of moles per mil, it would be, if it's millimolar, it would be, yeah, millimoles. So millimolar is describing millimoles per liter. So just as a comparison, 1,000 millimoles are equal to 1,000 millimolar is equal to 1 molar. So it's just another way of expressing molarity using prefix units. Does that make sense? Okay. Now, if you happen to need to solve and figure out the volume of solution that you need to add in a reaction, the volume is equal to the moles of solute over the molarity of the solution. So this is just rearranging the expression algebraically. Any questions on these equations? Now, of course, things are best learned via application. So let's do an example. So we're asked to determine the molarity of a solution obtained from 4.35 moles of potassium permanganate dissolved in enough water to make 750 milliliters of solution. Okay, what is the volume of our solution? What is the volume of our solution? What's our total volume? 750 milliliters. Now, is there a problem with this milliliters? Molarity, is it mole per mil or mole per liter? Liter. So let's do the conversion. In 1 liter, there are how many milliliters? Yep. Oh, whoops. I made a mistake. In 1 mil, there are 10 to the negative third liter. And the way that I can know that I made a mistake, the power of 10 always goes with what unit? The base unit. Okay, so that in turn gives us 0.75 liters. Okay, perfect. What about the moles of solute? How many moles of solute do we have? Yep, 4.35, and this is moles of KMNO4. So the molarity of our permanganate solution is the moles, which is 4.35 moles of KMNO4, potassium permanganate, over 0.75 liters of solution. So we have 4.35 over 0.75, and that in turn gives us a 5.8 molar solution of KMNO4. And it's important that you don't just write molarity. Molarity of what? This is really important because in solution, different components in the solution will have different molarities potentially. Does that make sense? So just like you put your mole labels, you also label your molarity. It will save you a lot of grief. Okay, any questions on this example before I let you loose on one for your own? Okay, so let's have you work on the following example. I'd like you to determine the molarity of a solution obtained when 20 grams of sodium hydroxide is dissolved in enough water to make 1.5 liters of solution. So you're going to need to convert to moles here, but you're capable of that. You just have to convert the 20 grams of sodium hydroxide. Everything may I see or 7? You said 20 over 40 divided by 1. Seems fine. Everything going okay? So to get molarity, we need moles over liters, right? So we have grams. Can we calculate moles from that? Everything going okay? I got 0.02. Yep. Now you just have to round it to the right number of sigma. Wait, round it? So the sigma, because it's only this, looking at your numbers, these have 3 sigma. Yeah. Ah, yes, that looks good. That's, yes, yeah, exactly right. Yeah, perfect. Yeah. Okay, I saw a lot of reasonable answers, so let's take a look at this problem. So we know that our volume of solution in this case is 1.50 liters. Okay, we know that our grams of solute are equal to 20.0 grams of NaOH. Okay? Can we calculate? Can we go from grams of sodium hydroxide to moles of sodium hydroxide? Can we do that conversion? Yes. So given we have 20.0 grams of sodium hydroxide, if we're going from grams to moles, what units will go on top? Moles. In 1 mole of sodium hydroxide, we have how many grams, roughly? What's the molar mass? Let's do that. Let's do that. Let's just make sure we're completely explicit on what's going on here. Sodium has a mass of about 23. Oxygen has a mass of about 16. Hydrogen has a mass of about 1. So that gives us a molar mass of 40 gram per mole, roughly. Does that make sense? Okay. So then, in turn, that gives us 0.500 moles of NaOH. The reason why I'm retaining 3 sig figs are molar masses exact or inexact. They're functionally exact. Like this number has like 10 sig figs behind it. So you're never going to be constrained by your molar mass sig figs. Now that we have the moles and the volume, we can calculate the molarity. So we take 0.500 moles of sodium hydroxide over 1.5 liters. Did we have to change anything about our units? Are we in units of mole per liter? Yeah. So then 0.5 divided by 1.5 gives us 1.50. Just to make sure our sig figs are aligned, we get 0.333 molar sodium hydroxide. And we report 3 sig figs because do both of our inputs have 3 sig figs? Yes. Always important just to make sure your sig figs are in order. Did that make sense to everyone? Okay. I saw a lot of these correct responses, so pretty confident we can move on now and tackle a slightly more complicated example. In this example, I want us to tell me what is the mass of solute dissolved in 2.5 liters of a 0.25 molar solution of copper 2 sulfate. I'll start us off with the first type of example of this form, and you'll do the second. So then, we know that molarity is equal to the moles of solute over the volume. We also know that the moles are equal to the molarity times the volume of solution by rearrangement, right? So given that we're starting off with the volume of solution, we're given that we are starting off with 2.5 liters of solution. And in the end, we want to report the grams of copper 2 sulfate. How do we calculate mass? What units do we calculate mass from typically? What was that? Molar mass. And what units do we start from? Moles, exactly. So we need the moles of copper sulfate. Now, do we have a conversion factor that allows us to go from the volume of solution to the moles of solute? Do we have a conversion factor? Looking at this above equation that we just wrote, do we have a conversion factor that allows us to go from the volume to the moles? Yes, yes, we do. And this conversion factor is our molarity. Our molarity allows us to convert between the volume of solution and the moles of solute. Wonderful. Okay, we're now ready to execute on this. So for this, we're starting off with 2.5 liters of solution. Since we're going from volume of solution to moles, what units need to be on top? Moles. So we have 0.25 moles of copper sulfate per 1 liter of solution. And then finally, if we're going from moles to grams, what units need to be on top? Grams. And have I already given you the molar mass? Yes. I wouldn't expect that on an exam, however. Okay, liters cancel, moles cancel, and we're left with grams of copper sulfate. So let's just punch that into our calculator. We have 2.5 times 0.25 times 159.61. And that in turn gives us 99.7 grams of copper sulfate. And let me check to see if we need to round. Yes, we do. We need to round it to 2 sig figs. So this is rounded to 1.0 times 10 to the second grams of copper sulfate. Now, why am I writing this number so awkwardly? Is there an easy way to write 100 with 2 sig figs? Sure. But if you write out with trailing zeros, those zeros wouldn't be significant. So for example, if we wrote out 100, we'd have 2 zeros that are not considered significant. So if you ever run into that situation, it's better just to write the number in scientific notation. Does that make sense? Okay. So with that first representative example out of the way, I'd like you to tell me how many grams of sucrose are present in 185 milliliters of 2.5 molar sucrose solution. This time I gave you the formula, but you're gonna have to do some heavy lifting and calculate the molar mass. And just watch your units very carefully for this one. So it's good. We recommend doing the molar mass calculation, just so that way, if there's an error, you can just follow it. Everything going okay? Yep, perfect. Everything going okay? Any questions? Any questions? questions? Anything going on? Oh, it's 10 to the positive side. Okay, since it's 100. Yep. Everything going okay? Yep, setup looks good. Everything going okay? Okay. Any questions? Yep, looks fine. Any questions? Okay. Everything going okay? The molarity is mole per liter. You need to convert your mole into liters. Does that make sense? Good. Everything going on? Any questions? So I saw a lot of reasonable answers provided for this section. So let's now talk about this problem, and let's talk about a few aspects of this problem. So first things first, let's take our formula and let's calculate our molar mass. Let's just have that piece of information handy. So to calculate our molar mass, we'll take the mass of carbon times the number of carbon atoms, plus the mass of hydrogen times the number of hydrogen atoms, plus the mass of oxygen times the number of oxygen atoms. So we have 12 times 12 plus 22 plus 11 times 16. And that gives us a molar mass of 342 grams per mole. Wonderful. Okay, now from here, we are given the volume of solution is 185 milliliters. So starting from the volume of solution of 185 milliliters, in the end, we want to be able to report the grams of sucrose. Now, where do we calculate the grams of a substance from? What units? Where do we get grams from typically? Moles, right? So we're going to get the grams of sucrose from the moles of sucrose. And then in order to calculate the moles of sucrose, in order to use our molarity conversion factor, what units does our volume need to be in? Liters. Okay, we now have our solution map in place, so we can now execute on the solution map. So we have 185 milliliters, and my question is, how many liters are there per milliliter? Yep, 10 to the negative third. Okay, now if we're going from liter to moles, how many moles do we have per liter? 2.5. We have 2.5 moles of sucrose. I always put my labels per 1 liter. And then finally, if we're going from moles to grams, what units go on top? Grams. So then we have 342 grams in 1 mole. And if we punch that into our calculator, 185 times 1 EE negative 3 times 2.5 times 342. That in turn gives us 158 grams, which because all of our inputs have how many sig figs? 3. Okay. Does that make sense to everyone? Yes, yes, if you're, yes. No, that is perfectly important to point out. The reason why I didn't include the label in this case is it asked in the question for the grams of sucrose, but there is no reason not to put the label. You're 100% correct. And this is important especially, and this is a good point to bring up, if you're handling multi-step problems, the more labels you have, the easier it is for you to go back and audit your work. So yes, that's exactly good practices. Thank you for bringing that up. Any other questions on this example? Okay, So let's talk about another form of question where let's suppose you want to make a 0.15 molar solution of potassium hydroxide in water. If you start with 40 grams of potassium hydroxide, what total volume of solution should you prepare? Okay, so let's suppose you want to use all of this potassium hydroxide so it doesn't go bad, for example, and you want to make a solution out of it. Looking at this problem, we know that we want our molarity to be 0.15 molar. We also know that our grams of solute is equal to 40.0 grams, right? Our goal in this problem is to figure out the volume of our solution, okay? So the way that we're going to go about doing this is we're going to start with the grams of solute. We're going to start with the grams of solute, and our goal is to end up at the volume of our solution. How can we calculate the volume of solution using molarity? What units will we go through? How do we get volume using molarity? Exactly. So we need to go to moles of solute, in this case NaOH. Perfect. We now have our solution map, and now we can execute on it. Notice, I'm not writing equations down here. I'm just looking at my units, and once I have the units, I don't actually even have to understand how any of these equations work. If the units cancel, you'll be able to go from the starting units to the ending units in the correct form. Okay, so then starting with 40.0 grams of potassium hydroxide, if we're going from grams to moles, what units are on top? Moles. So in 1 mole of KOH, potassium hydroxide, we have how many grams? Let's calculate it, okay? So for our molar mass, we take the mass of potassium, which is what? Do you have a copy of your periodic table? Don't be shy to pull out your periodic table. What was that? 39, yep. So 39 grams plus the mass of oxygen, which is 16, plus the mass of hydrogen, which is 1. So we have 39 plus 16 plus 1. That gives us 56 grams per mole of KOH, potassium hydroxide. Always bring your periodic table to class. Always have it handy. It's the central toolbox needed to solve chemical problems. Okay, now if we want to go from moles to liters, what units go on top? Liters, okay? So in 1 liter of solution, we have how many moles based on our molarity? Yep, 0.15 moles. And this is moles, more specifically, of KOH. Okay, punching this into our calculator, we have 40 divided by 56 divided by 0.15. That in turn gives us 4.8 liters. The reason why I rounded to 2 sig figs, how many sig figs does our molarity have? 2. Any questions on this example? If not, I will let you loose for a second set of examples. Okay. So I'd like you to process, if you want to prepare a 0.45 molar solution of copper chloride in water, if you start with 50 grams of copper chloride, what total volume of solution should you prepare? Any questions? Any questions? Oh, okay. Any questions? Okay. Any questions? Okay. Everything going okay?
Yeah, we'll just write the question.
Okay. Everything going okay?
Okay.
Everything going? Yeah. That's good. Everything going okay? Okay. Any questions so far? Okay, your setup looks good and your molar mass calculations correct.
So I see a lot of reasonable setups. Everyone's on the right track. All that's left is to punch things into the calculator. So let's talk through this problem a little bit and let's highlight the key features of this problem. So we are starting off with the grams of solute, the grams of copper chloride, and in the end, we want to be able to report the liters of solution. So then, in order to calculate the liters of solution, given our molarity, what units do we need to be in? What units do we need to have? Moles, yep. So in this case, we need to go from grams of copper chloride to moles of copper chloride to liters of solution. Just to make sure we're matching our true solution map format, we're going to use our molar mass to go from grams to moles, and we're going to use our molarity to go from moles of solute to liters of solution. Okay, so let's continue on from there. So let's calculate the molar mass of copper chloride. What is the mass of copper? Yep, 63.5 if we want to be a little bit more specific, just because all of our inputs have at least 3 sig figs. Okay, what is the mass of chlorine? Yep, 35.5 grams. And how many chlorine atoms do we have? 2. Okay, let's add that in our calculator. 63.5 plus 35.5 times 2. That in turn gives us 134.5 grams per mole of copper chloride. Perfect. So we've laid the groundwork to complete this problem now. All we have to do is execute. So if we have 50.0 grams of copper chloride and we're going from grams to moles, what units are going to be on top? Moles. So in 1 mole of copper chloride, we have how many grams? Did we just figure that out? 134.5. Okay, and if we're going from moles to liters, what units need to be on top? Liters. So in 1 liter of solution, we have how many moles of copper chloride? 0.45. Okay, perfect. Now all we have to do is punch it into our calculator. So we have 50.0 divided by 134.5 divided by 0.45. And that in turn gives us 0.83 liters. Why do we round to 2 sig figs? What's going on here? Our molarity has how many sig figs? 2. Exactly. Everyone comfortable on molarity calculations so far? Yes.
So I know you probably answered this before, but whenever we're getting the numbers off of your table.
Yes, those numbers have such an excessively large number of sig figs that they will almost never constrain your precision. They have at least 8 to 10 sig figs in like the full atomic masses that have been determined. Yeah.
So if we round it, it's not a problem.
Yeah, so in general, you want to make sure your atomic masses have more precision than any of your inputs. So that way you're not truncating digits or removing precision using your molar masses. Does that make sense?
Yeah.
Perfect. So what we're now going to talk about, and this is really important for understanding net ionic equations. This same process will be used when we discuss net ionic equations. We're going to try to get a sense of how do we describe the concentration of ions in solution. Now, why is this So much different than describing the concentration of compounds or molecules. Well, we've established that soluble ionic compounds dissociate to give their component ions, right? They break apart, just like in our sodium chloride example, right? It's not sodium chloride sitting together as one chunk. Sodium chloride in solution is found as ions. Now, as a consequence of that, the moles of ion in solution per mole of ionic compound is based on the chemical equation. So, for example, let's dissect sodium sulfide. And let me draw a picture. So we have our sulfur. We have our 2 sodium ions. So my question to all of you, if we have 1 mole of sodium sulfide, how many moles of sodium do we have per mole of sodium sulfide? 2. Where does this ratio come from? What do we call this ratio that we've used time and time again? Not quite the empirical formula, but it's a ratio based on the formula, so it's the formula ratio. Right? And are we comfortable using formula ratios? We've used it to calculate numbers of atoms, right? We've also even used it to calculate numbers of ions in a compound. And that's all you're doing. You're reading the formula and using the formula ratio to indicate the number of each ion found in your ionic compound, and as a result, the number of ions that we get in solution, right? So this is actually something that we've seen before. So for example, if we have sodium sulfide and we start with 1 mole of sodium sulfide, let's calculate the moles of sulfide. So in 1 mole of sodium sulfide, how many moles of sulfide do we have in 1 mole of sodium sulfide? What's our mole to mole ratio? What's our formula ratio? How many sulfurs do you see? 1. So that in turn gives us 1 mole of S2- in solution. So the concentration of ions will not always be the same as the concentration of your ionic compound. Does that make sense? Okay. Now, how do we use this idea? How do we use this idea? Well, just keep in the back of your mind, ionic compounds dissociate, okay? We're going to use this in a moment. So, I'll start us off with an example. A researcher made a 20 millimolar solution of sodium nitride, and they want us to calculate the molarity of each ion in this solution. Okay, so let's start off. I have a 20 millimolar solution of sodium nitride. What that is telling me is that I have 20 instead of moles. If it's millimolar, instead of 20 moles per liter, I have 20 millimoles per liter. And if we're really insistent on writing this in terms of mole per liter, how many moles are present in a millimole? What does the milli prefix represent? Yep, 10 to the negative third. See, the base prefix system is universal throughout science. And the reason why we use millimoles is because millimoles are typically quantities handled on the milligram scale, which is where most quantitative and interesting chemistry, in my opinion, is done. Okay, so then punching this out, so we have 20 times 1 EE negative 3, so that gives us 0.0200. Since this is 20.0, this has 3 sig figs, so I do need to respect that. Does that comment make sense to everyone on why I'm respecting the sig figs of my input when I do a conversion? 3 sig figs in, 3 sig figs out. Okay, Now we're ready to dissect the formula ratio. So let's start us off. So reading through our formula, my question, so let's write this instead of molarity, let's write this in more useful units of moles of sodium nitride per 1 liter. So that way we can actually get at and do a mole to mole conversion. So if I want to figure out the molarity of my ion, I need to go from moles of sodium nitride to moles of, if I need to figure out the molarity of an ion, I need to convert from moles of sodium nitride to moles of my, let me put it in more tangible terms. If I wanted to go from the moles of sodium nitride per liter to the moles of sodium per liter, can I do that using my formula ratio? Yes. So then, if I'm going from moles of sodium nitride to moles of sodium, what units need to be on top? Okay, so how many moles of sodium plus ion do we have per mole of sodium nitride? 3. 3 to 1. And that in turn gives us 0.06 moles of sodium plus in 1 liter. You can also say we have 0.06 molar sodium plus solution. Let's repeat this idea. Let's repeat this concept with a new compound. Or let me rephrase, for the second ion in this compound. So we have 0.0200 moles of sodium nitride per 1 liter. If we want to go from moles of sodium nitride per liter to moles of nitride per 1 liter, what units need to be on top? Moles of what? Nitride. So we have 1 mole of nitride per 1 mole of sodium nitride, and that in turn gives us 0.02 molar nitride solution. Does that make sense? Okay. So what I do want to emphasize is these types of problems can be combined with nomenclature. So if you don't know how to write the formula from the name, you'd be stuck. So in order to give you a representative example of this, we're going to talk about a very similar type of problem, the exact same form, except this time you have to generate the formula from the name. So cesium sulfate. Would someone like to volunteer a formula for cesium sulfate? Yes, exactly right. CS2SO4. So cesium, it's a 1A element, has a +1 charge. Sulfate, 2-. That you'll have to know that sulfate is SO4, 2-. We cross our charges, we get CS2SO4. So without the formula, you'd be stuck for this problem. So now that we have the formula, you're able to do mole-to-mole conversions using our formula ratio. So I'll give you a few moments to work on this, and then we'll come together as a group to discuss. Everything going okay? Everything going okay? Everything going okay? Everything going okay? Looks good. Everything going okay?
Yep, exactly right. Exactly right. Yep, yep. And now you can do mole to mole conversion. Yes, yes, yes. But rank the label. This is the moles of cesium sulfate. Any question?
So we're gonna grade 2, 3, right?
What was
No, we just, so it's,
that? Wait. What ions are we making? What ions do we serve? So the ions are cesium and sulfate. So sulfate doesn't break apart.
oh, okay, so.
Yep. Everything going okay? Looks good so far.
So because we're trying to find.
Yes, yes. Yes, exactly.
Thank you.
So I saw a lot of reasonable solutions here, but I just want to emphasize one thing that's really important. If we have cesium sulfate dissolved, what ions are we going to get in solution? Did we already list our ions when we came up with this formula? Yes. So what ions are we going to get? Yep. So we get cesium plus, and how many of them? 2. And we're going to get SO4 2 minus, and how many of them? 1. This is where the formula ratio comes into play, and I just don't want you to forget this idea. Okay, so starting off, we have a 10 millimolar solution that we can write as 10 millimoles of cesium sulfate in 1 liter. We know that there are 10 to the negative third moles in 1 millimole of cesium sulfate. So that in turn gives us 0. So this is all 10.0. So 3 sig figs. So we have 0.00100 moles of cesium sulfate. Whoops. Let me rewrite this over here. So we have 0.00100 moles of cesium sulfate in 1 liter. And now, can we use our formula ratio to do some mole to mole conversions? Yep, we can. So let's do the first of which. How many moles of cesium plus do we have in 1 mole of cesium sulfate? What's our mole to mole ratio? 2. So then that gives us, we have a 0.00200 molar solution of cesium plus. Would someone like to volunteer, since our mole to mole ratio for sulfate is just 1 to 1, what's the molarity of our sulfate solution? Yes, exactly right. Does everyone see why the sulfate concentration is the same as the cesium sulfate concentration? Perfect. Any questions on this example? Okay, let's keep going then. Now, for dilution, a critical feature of dilutions. So what is dilution? So for example, you're taking a solution that contains solvent and some dissolved solute. And in dilution, what we are doing is we are adding solvent. That is all we are doing. We are just adding solvent, okay? So in turn, we have a larger volume of solution with the same amount of solute. So 1, 2, 3, 4, 5, 6. So the solute, the moles of solute is unchanged. if the moles of solute changes, or if you're adding something other than just pure solvent, you're not doing a dilution. You're doing an entirely different process. You're just mixing things together. And those are handled mathematically in a different way. Does that make sense? Okay. Now, why does this matter? Why do we care about this? Well, we're able to establish the moles in any dilution. The number of moles of solute does not change. Only the concentration changes. So the moles of solute initial must match the moles of solute final after your dilution. From that, we also know that the final volume is just the volume of the two solutions that you've combined, added together, right? If you mix 10 mils of water and 100 mils of solution, your total volume is 10 plus 100, right? That's simple enough to see. Now, we can figure out and we can write the moles present, moles of solute present, just by taking molarity times volume, right? We can calculate moles by taking molarity times volume. Now, since the mole, so like our initial moles are the initial molarity times the initial volume, our final moles are the final molarity times the final volume, right? And since the moles do not change, are these two expressions equal to each other? If the moles do not change, if the moles are equal before and after a dilution, are these two expressions going to be representing the same number? Yes. So then we can directly relate the molarity and volume of our solution before and after we perform a dilution. Does that make sense? Okay. So let's define our terms. So in the equation, M1V1 equals M2V2. M1 is the initial concentration before dilution. V1 is the initial volume of our solution. M2 is the final concentration, and V2 is the final volume of our total solution. Does that make sense? Okay. So what we're going to do is we're going to look at an example. And let's try to apply this dilution equation to solve problems. So we're asked how many liters of 20 millimolar potassium dihydrogen phosphate stock would be required to make 5 liters of solution that is 5.0 millimole. Okay, not too bad. So what is our volume initial? What is our V1? Do we know what V1 is? Do we know our initial volume, or is that what we're trying to figure out? Yeah, so let's put a question mark. Do we know our initial molarity? Do we know the molarity of the solution we're going to dilute? Yes, what is it? What was that? What is the molarity of the solution we are going to dilute? 20, yeah. So 20 millimolar. Okay, let's use a different color. What is our final volume? What's the final solution volume that we want to end up with? 5 liters or 5.0 liters. And what is our final molarity of that solution? Yep, 5.0 millimolar. Okay, perfect. We're now ready to execute on this expression. So we know that V1 times M1, which is 20 millimolar, is equal to V2, which is 5.0 liters, times M2, which is 5.0 millimolar. That means solving for V1, we have 5.0 liters times 5.0 millimolar over 20 millimolar. Our units of millimolars cancel, and we're left with units of what for volume? Liters. As long as your units cancel, this expression would work. So, but you just want to be careful that you're writing down the units and seeing what units are left after things cancel. So we have 5 times 5 divided by 20. And that in turn gives us 1.25 liters. So we're going to need to dilute 1.25 liters. So just to show you a picture of how this would be done. So we'd add 1.25 liters of our 20 millimolar solution. And then we would add water. We would add water all the way up to the 5.0 liter line. So this would take roughly 3.75 liters of water. And when I say fill to the line, what flask do we use typically for dilutions to a target volume? Volumetric, exactly. Does that make sense, how this works? This is a common thing that you have to do as a lab tech. All of our instructional aides do these calculations on a day-to-day basis and need to make solutions. It's an important skill to know because it makes you quite useful in the lab as an undergraduate. Okay, I want you to tell me in this next problem how many liters of 6 molar sodium hydroxide would be required to prepare 500 milliliters of 0.2 molar sodium hydroxide. And if this calculation looks familiar, it's no coincidence. I want to make sure we understand how to do lab-based calculations. Oh, I see. There's a decimal beginning. Yes, yes, that's it. Okay. Sorry, I didn't see this. Everything going okay? Let's see. So I put 500. So you're not solving your, so you have your M1. Yeah. So solving for V1, take the V2 times the molarity 2 over molarity 1. So try writing out the expression and then plugging in each of your numbers. The expression. Wait, so it's V2 times M1 V1 equals M2. Everything going okay? Okay. Everything going okay?
Yes.
Okay. Any questions? Yeah, you're set up. Any questions? Yeah, exactly that. Okay. You're set up. So I see a lot of reasonable responses. So let's now come together as a group to discuss this problem. So I like to label what I know. So what is our initial molarity? What solution am I diluting? 6 molar. Yep. Do I know my initial volume, or is that what I'm trying to figure out? Yep. So I'm going to put a question mark. Do I know my final molarity? Yep, 0.20 molar. And do I know my final volume? 500 milliliters. But let's now convert this into liters since I want my final answer to be in liters. So so how many liters are in 1 milliliter? Yep, 10 to the negative third. So that gives us 0.5 liters. Because those trailing zeros, are they significant? No. So now plugging into our expression, we know that V1 is equal to M2 V2 over M1. Is everyone comfortable with me rearranging the equation before I plug in the numbers? Let's now substitute the numbers here. We have 0.20 molar times 0.5 liters over 6.0 molar, and that in turn gives us 0.2 times 0.5 divided by 6.0. That gives us 0.0166 liters, which we then round to 0.02 liters. Does that make sense? Is everyone more comfortable with these kinds of dilution calculations? And why did we round to 1 sig fig? How many sig figs does our volume input have? 1. 0.5 liters has how many sig figs? 1. Always watch your sig figs, especially for lab calculations. Is everyone comfortable with this? Can we move on to the next topic? Okay, let's keep going then. So remember how I discussed this idea that for solutions, you need to be careful to ensure, first and foremost, that your ionic compounds are actually soluble. I've had people often, I'd ask them a question, calculate the concentration of ions for an insoluble compound, and then they go through all this work only to realize at the end, it's nothing getting in solution if it's insoluble. Don't worry about this for now, just be aware of this for later and on the exam. Now, you have to be very careful when mixing solutions with the same ion present. Now, when there's the same ion present in multiple solutions, are you doing a straightforward dilution anymore? Are you doing a real, genuine dilution anymore? Are you just adding solvent, or are you adding more ion? You're adding more ion. So you cannot use the dilution equation. You cannot, okay? So I'm going to write, so M1 V1 equals M2 V2. Just don't use it. Doesn't apply in this case. Won't work. Why? Are our moles staying constant, or are our moles changing? They're changing, exactly. So for example, if you mix a liter of 1 molar sodium chloride with a liter of sodium bromide. Now, just taking a look, and I really like to do this from a pictorial perspective, since if you look at the picture, it becomes really obvious the problem. If I combine these solutions together, I see 1 mole of sodium in my sodium bromide, 1 mole of sodium in my sodium chloride solution. How many moles of sodium will I get out in the end? 2. That's why we see 2 pictures. So then, the moles of sodium is not staying constant. So let's take this example. Let's look at this example in detail where we mix 1 molar sodium bromide and 1 molar sodium chloride, and we're mixing 1 liter of each. Okay. So the first goal, whoops, I should not have the negative charges there in this case. So our first goal is to convert the molarity of each solution to the moles of ionic compound, okay? So if I have 1 mole, let me write this. So if I have 1 mole of sodium bromide in 1 liter, in order to calculate the moles, I take my molarity times my volume. And what's my volume of the solution? 1 liter, okay. So just as a reminder, moles are equal to molarity times volume of solution. So we have 1 mole of sodium bromide. Okay. So, everyone clear on where we got this 1 mole from? We can repeat this exact same process for sodium chloride. So we have 1 mole of sodium chloride per 1 liter times 1 liter, and that in turn gives us 1 mole of sodium chloride. Perfect. That's wonderful. So we have the moles of each ionic compound. Now, the next step in this process, we want to calculate the moles of each ion in solution, and then calculate the total moles of ions in all solutions. Finally, we calculate the total volume, and we can calculate the molarity. So let's now execute on our current plan. Let's calculate the amount of each ion found in each ionic compound. So let's execute on that idea. So we have our sodium chloride and our sodium bromide solution. So let's do a representative calculation. If I have 1 mole of sodium bromide in my solution, how many moles of sodium plus do I have in 1 mole of sodium bromide? What's our mole to mole ratio? 1 to 1, right? So we also have 1 mole of sodium plus. Okay. So we have completed the majority of our calculations for the moles of each ion. So let's list out each of our solutions and let's list out the moles of each ion. So for sodium bromide, I have 1 mole of sodium, 1 mole of bromide. For sodium chloride, I have 1 mole of sodium and 1 mole of chloride, right? From our formula ratio and from the moles of each. Does that make sense? Okay. Now, if I want to look at my total moles, so for sodium, if I want to look at my total moles of sodium, if I add the moles of sodium found in each solution together, what do I get? What's 1 plus 1? 2. So I have 2 moles of sodium. How many moles of bromide do I have in both of my solutions? 1. And I have 1 mole of chloride. Okay. Perfect. So I have my total moles established. I have my total volume. So what's my total volume? If I mix 1 liter plus 1 liter, what's my total volume going to be? 2 liters. Okay. Now, all I have to do to calculate the molarity, of each ion in my solution is to divide each of my total moles by the total volume. Does that make sense? This is known as a mole volume table, and it's a fast way to calculate the concentration of ions found in each solution. So then I have 1 mole of sodium plus per 1 liter. I have 0.5 moles of bromide in 1 liter, and I have 0.5 moles of chloride in 1 liter. Does that logic make sense to everyone? I calculated my total moles from the moles present in each solution. I calculated the total volume by adding up the volume of each of my solutions, and then I divide my total moles, each of them, by my total volume. That allows me to get the concentration of each ion in solution. Does that make sense? Let's do another example. Let's do another example where I work through it longhand from start to finish, so that way we are comfortable with these types of problems. Just give it 1 moment. Okay. Here we go. So in this problem, we're asked to calculate the concentration of sodium plus when 0.1 liters of a 0.5 molar solution of sodium phosphate is mixed with 0.2 liters of 0.1 molar potassium acetate. Okay? So we're going to need to consider and write out each of the formulas for our compounds and then calculate the total moles of ion in each solution and the total volume. Okay, so in solution 1, sodium phosphate. We first need a formula here. What's the formula of sodium phosphate? Na3PO4. We have sodium plus, phosphate minus. We cross our charges. That gives us Na3PO4. Okay, it's 0.1 liters of a 0.5 mole per liter solution. Can we calculate the total moles of sodium phosphate by taking the molarity times the volume. Can we do that? Do we have the tools to do that? Can we get moles from molarity and volume? Yes, all we have to do is multiply them. So then we have 0.1 times 0.5. That in turn gives us 0.05 moles of sodium phosphate. And now what we're going to do is we're going to break down this moles of sodium phosphate to get the moles of sodium. So we have 0.05 moles of sodium phosphate. And my question to all of you is, how many moles of sodium plus ion do we have per mole of sodium phosphate? What's our mole to mole ratio? 3 to 1, exactly right. And that in turn gives us 0.15 moles of sodium plus in 1 liter. Or let's avoid that 1 liter, just 0.15 moles of sodium plus. We still need to calculate the total volume. Okay, let's look at potassium acetate. Would someone like to tell me the formula of potassium acetate? Yeah. KCH3CO2 or C2H3O2. Both are fine. I just like this form because it allows me to recognize that it's an acetate and allows me to recognize its structure. Okay, we know that we have 0.2 liters, and we know that its molarity is 0.1 moles of potassium acetate per 1 liter. Now, is there any sodium ion found in potassium acetate? Do we see any sodium symbol? No. So do we have to go through the step of calculating the moles? Do I have to bother with that if I want to know the concentration of sodium? Do I have to bother with that? No, not at all. But what I do need, I have my moles total of sodium plus. I know it's 0.15 moles of sodium plus. Now I need to figure out my total volume. So what is the volume of each of my 2 solutions? What's the volume of my sodium phosphate solution? What was that? 0.2 liters is potassium acetate, yes, but we need to note that. What's the volume of our sodium phosphate? Reading through the problem, what volume of sodium phosphate did we mix? 0.1 liters, exactly right. So then we get a total volume. Whoops, give it 1 second. Sometimes it gets a little laggy when a lot of things are written. Okay, so that gives us a total volume of 0.3 liters. Finally, the molarity of sodium plus is our total moles, which is 0.15 moles of sodium plus over our total volume, which is 0.3 liters. So if we take 0.15 divided by 0.3, we get a molarity of sodium of 0.5 moles of sodium plus per 1 liter, or a 0.5 molar solution of sodium plus. Does that make sense? So in this case, we didn't even have to add them together. We just calculated the moles of our ion and divided by the total volume. I would prefer you use this method by default over M1V1 equals M2V2 as it's less error prone. So as the last example that we'll be doing today for this chapter, and a good example to wrap up on, we'll be tackling the following example. And this should take us at least 15 to 20 minutes. I want us to calculate the concentration of ions in solution obtained from a solution by mixing 175 mils of 0.1 molar potassium phosphate with 27 milliliters of potassium chloride. So just like before, you need to calculate the total volume and you need to calculate the total moles of ions found throughout both solutions. So I'll have everyone start with the chloride example, as that's the easier of the two, and then you can move on to the potassium example. Everything going okay? Just like we did in Dissect, we calculate the total, calculate the total, and add them together. Everything going okay?
I just set it up.
Okay. Everything going okay? Assuming the volumes be added together to get the total. Because for some solutions, actually, the volumes aren't added. And that's due to entropy effects, etc. So, yeah. Everything going okay? So essentially, what we did is we calculated the moles of that compound. We drew the moles behind. We figured out that this compound doesn't have any sodium ions, so we don't need to bond with it. What we need is more with the total. Once you have the total moles, just divide by the total. You got it? Everything going okay? Okay. So, table of the total moles for each ion, the total moles, and then actually you divide by it. Okay. That's the way out. Just like we did. Sodium chloride, sodium chloride. Everything going okay? Yeah, you calculate the moles. Are there any other chloride sources? So is KCl the only compound that is chloride? So it's a KCl and potassium phosphate. So yeah, KCl is the only. So you're correct. Once you have the moles, you're going to divide by the total volume of all solutions. Does that make sense? If we're everything going on, well, can we calculate the moles of each mole for each ion? Yeah. So then let's calculate the moles of each ion in each solution. We add up the moles for the same ion together, and then we divide our total moles by the total volume. Oh, okay. Does that make sense? Okay. Perfect. Everything going okay? Okay, so you have your total volume. Yep, looks good. Oh, for milliliters, it's times 10 to the negative 50. So this value, this is too large, it should be small. It should be 0.027. Everything going okay? Yeah, looks good so far. Everything going okay? So it's just sodium chloride, sodium chloride. I'll start by calculating most of each item, then calculate the most of each item, then add the total, add it together, divide by the total. So first calculate the total volume of the compound, right?
solution. Take the molarity unit to side, divide total moles, whole solution. Any question? What do you calculate? So this is the moles of. But the volume of KCl is 27. Yeah. So I saw a lot of reasonable responses for the chloride section. So I'm just going to show you the general protocol I like to use. First things first, I'm going to figure out the moles of potassium chloride by taking my molarity, which is 0.2 moles of potassium chloride in 1 liter, times my volume of 27.0 milliliters, times the conversion factor of 10 to the negative third liter per milliliter. That in turn gives me a moles of KCl equal to 0.00540 moles of KCl. Then what I'm going to do is I'm going to use my formula ratio and how many moles of chloride are present per mole of KCl. What's our mole to mole ratio? 1 to 1. So that tells me I have 0.00540 moles of chloride. How many moles of potassium do I also have from KCl? Is it the same? Is it also a 1 to 1 ratio? Yes, so I'm going to write that down as well. We also have 0.00540 moles of potassium. So this is how you make what is known as an ion volume table, okay? Now that I have my amount of each ion, looking at potassium phosphate, do I see any chlorines in potassium phosphate? Do I see any chlorides in potassium phosphate? No. So then, the only thing I need to care about is my total volume. So I'm going to calculate V total now by taking 175 milliliters plus 27 milliliters times 10 to the negative third liter in 1 milliliter. And that, one moment, 175 plus 27 times 1 EE negative 3. That in turn gives us 0.202 liters. So then, to finish this off, if I want to calculate the concentration of chloride, all I do is take my moles of ion in all ionic compounds and divide it by our volume. So 0.0054 moles over 0.202 liters. And that in turn gives us a concentration of chloride, 0.0054 divided by 0.202. That gives us a concentration of chloride of 0.0267 molar. Does that logic make sense? Calculate the total moles, calculate the total volume, then divide. Now, I have started you off with an ion table. You're going to need to use these moles of ions from potassium chloride, and then you're also going to need to calculate the moles of ion in potassium phosphate. So try to figure out the concentration of potassium at the end, and to do that, you're going to need the total moles of potassium in all solutions. So take a shot at that, and we'll come together to discuss. Going on. So you're going to use this for potassium phosphate. And then looks like all of your moles, we're going to write it up, add together, so we actually say, is that awesome? Yeah. Everything going okay? So first we can calculate the moles of KCl and molarity and then the moles of the compound. Here in the same process for potassium phosphate. Molarity and volume potassium phosphate. Potassium phosphate. Potassium.
So instead of using this, oh,
Everything going okay? Yep. You have the moles of potassium. Yep. And now you're going to do the same thing for KCl. Yep. Everything going okay? Yeah, these other get exactly right. Perfect. Yep. Perfect. Everything good? It's setup looks good. Your setup looks good, but it's the wall is very nice for potassium phosphate. But otherwise, this part's fine. You just need to change your wall calculation. Yes. Oh, well, let's Let's fine. And get out of together. Yeah. Oh, but the moles of potassium phosphate is not the same as the moles of potassium. It's not the potassium. Yeah. What's going in the military by 3. How'd it go? Yes. No. That's correct. And then you add these two together. But what volume of potassium phosphate do we have? 175. Okay, so to wrap up this chapter, we got through the entirety of chapter 5 today almost, but let's finish off this problem, and let's finish off this problem strong. Okay, first step, we're going to need to figure out the moles of potassium phosphate. And what is the molarity of our potassium phosphate? What's the molarity of potassium phosphate? 0.1. So we have 0.100 moles of potassium phosphate per 1 liter. And what volume of solution do we have? Yep. Which we can write as 0.175 liters. Is everyone following me so far on where I got the moles, molarity and volume to get the moles from? Now we have the moles of potassium phosphate, which is equal to 0.1 times 0.175, which gives us 0.0175 moles of potassium phosphate. Okay, From here, what we're going to do is we're going to break this down into moles of ion. So I want to figure out the moles of potassium, since that's what I'm being asked. So I take 0.0175 moles of potassium phosphate. And my question is, how many moles of potassium ion do we have per mole of potassium phosphate? 3. Okay. So our moles of K plus, whoops. So our moles of potassium plus are equal to 0.0525 moles of potassium plus. I also have potassium from my potassium chloride of 0.0054 moles of potassium plus. So then, to calculate my total moles, I simply add the moles of potassium in each solution together. Does that make sense? Does everyone know where I got this 0.054 from? I got it from my KCl calculation. These are the moles of potassium from KCl. Okay, that in turn gives us a total mole of 0.0579 moles of potassium. So then, if I wanted to calculate the molarity, or the concentration of potassium plus, I take the moles, which is 0.0579 moles of potassium plus, and I divide it by our total volume. And have we already calculated our total volume? 0.202. We already calculated our total volume. So let's just plug that in. And that in turn gives us a molarity of 0.287 molar potassium plus. Does that make sense? Any questions on this example? So just to recap all the way from the start. So first things first. If we're asked to calculate the concentration of chloride, we calculate the moles of KCl. From the moles of KCl, we can calculate the moles of each ion, right? Then we calculate the total volume. We look at all the sources of chloride, and we divide the total moles of chloride by the total volume. We did that. It went swimmingly. That was fine. Now, for potassium, there are multiple compounds that have potassium, right? So we need to add up the ions of potassium produced for each compound. So from potassium phosphate, we calculated the moles of potassium phosphate and then converted to the moles of potassium. From the moles of potassium, we calculated our total moles by adding up the moles of potassium generated from each ionic compound solution. Does that make sense? Once we have our total moles of potassium, to calculate the molarity, all we do is take our total moles of potassium and divide it by our total volume. You should be able to do an example of similar or greater difficulty of this form on the exam. Well, since we finished chapter 5, we'll start chapter 6 on Tuesday. Please have the chapter 6 notes ready and prepared. Yes.
What did you get? 0.0175. This is the, by multiplying these two.
Oh, these two?
Yeah.
Oh,
So
okay.
it's this down here.
Oh, got you.
Yeah.
So we got that number from here.
Yes.
And this is, oh, this one?
Yeah, I just converted it.
Oh, so you just
Yeah.
put the zero.
Yeah.
Oh, okay.
Yeah.
Do we have to do that? Or
So it's essentially the fact that to go from, 175 times 1 e negative 3, this converts from milliliters to liters.
Oh, got you.
Yeah.
Oh, okay.
Yeah.
You converted because
Yeah.
it was
Yeah.
more than
Yes.
so correct.
Does that make sense?
Yeah.
Perfect.
So we didn't have to divide by the total mass with chlorine because it's only present in one.
You don't have to add the moles together because it's only present in one.
Oh,
You do still have to divide by the total volume in both.
oh.
Yeah. Does that make sense?
Sorry, I just
No?
I'm still burnt from my calc test.
No problem, no problem. Yep, see you on Tuesday.
But now, like, since now that I got that test over with, now I can go back in chem mode.
That's good, because we're approaching one of the more difficult chapters. Chapter 6 is going to be the most
What is that? Geometry?
stoichiometry and balancing equation.
And that's it'll stop there and then the event? Or still keep going?
Yeah, about there. We may get to titration.
Tomorrow,
And that may be on the
you
exam.
want me
Since
to
it's the type of
Saturday?
stoichiometry.
Saturday.
Did it go okay?
Yeah, this part I do get.
Okay.
We didn't cover this much on the answer. I don't remember.
This one? This example? I think we did it in 100 too.
Those were the X3, right?
Yeah, that's different.